Filtering approaches like the extended Kalman filter suffer from quadratic complexity in the number of states, making large-scale simultaneous localization and mapping computationally intractable. GraphSlam fundamentally shifts the problem from sequential state estimation to a global batch optimization. Instead of propagating uncertainty forward, we model the environment and trajectory as a sparse graph structure. This structure consists of nodes representing robot poses or landmarks and edges representing spatial constraints derived from sensor measurements. The core objective is finding the configuration of nodes that minimizes the total error across all constraints, effectively solving a large, nonlinear least squares problem. This paradigm allows for efficient handling of massive datasets and ensures global consistency, especially when revisiting previously mapped areas. In the standard pose GraphSlam formulation, nodes exclusively represent the robot's pose at discrete time steps, typically defined by a 3-dimensional vector for 2-dimensional space or a 6-dimensional vector for 3-dimensional space. Edges connect these nodes, encoding relative transformations between poses. These relative transformations are derived primarily from odometry or visual inertial measurements. A key advantage of the pose graph is its reduced dimensionality compared to full SLAM, which includes explicit landmark nodes. The measurement model provides the mean and covariance of the relative transformation, defining the strength and uncertainty of the constraint edge. This structure naturally leads to a sparse Hessian matrix during optimization, crucial for computational efficiency.
GraphSlam minimizes a global cost function, often formulated as the sum of squared errors weighted by the information matrix. The error term, or residual, for any constraint edge is the difference between the measured relative transformation and the transformation predicted by the current estimates of the connected poses. Mathematically, we seek the state vector x that minimizes the sum over all constraints I of the residual vector transpose multiplied by the information matrix omega sub I multiplied by the residual vector. The information matrix, which is the inverse of the covariance matrix, dictates how strongly a specific measurement influences the final solution. High certainty measurements correspond to large information values, pulling the graph configuration more strongly towards that constraint. Constraints are categorized into odometry constraints and loop closure constraints. Odometry constraints link sequential poses, providing local consistency based on wheel encoders or inertial measurement units. These constraints typically have high uncertainty perpendicular to the direction of motion, reflecting wheel slip or integration drift. The information matrix omega quantifies this uncertainty. For a 2-dimensional pose, omega is a 3x3 matrix. A fixed initial pose constraint, often called a prior, anchors the entire graph, preventing translational and rotational drift of the entire structure. Without this anchor, the optimization problem is ill-posed, exhibiting a null space corresponding to rigid body transformations. Without loop closure, the accumulated error from odometry constraints causes the estimated trajectory to drift significantly over long distances, resulting in globally inconsistent maps. Loop closure is the process of recognizing that the robot has returned to a previously visited location. This recognition generates a non-local constraint edge in the graph, connecting two temporally distant pose nodes. This new edge introduces a powerful constraint that forces the intervening trajectory segment to conform to the known relative transformation between the start and end points of the loop. This mechanism is essential for achieving metric consistency and bounding the growth of positional uncertainty across the entire map.
Detecting a loop closure requires robust place recognition, typically achieved using visual or LiDAR data. Visual methods often employ techniques like bag of words, where image features are quantized into a vocabulary, allowing for rapid comparison of current and past scenes. Once a potential match is identified, geometric verification is necessary to confirm the spatial relationship. This verification involves matching local features, such as scale invariant feature transform or oriented fast and rotated brief, between the two poses and calculating the relative transformation using techniques like random sample consensus. Only verified matches with sufficient inliers are accepted as valid loop closure constraints. A successful loop closure detection yields a relative transformation T subloop and its associated covariance matrix sigma subloop. This information is integrated into the graph as a new edge connecting the current pose node P sub I and the recognized past pose node P sub j. The residual function for this new edge is calculated identically to the odometry residual, comparing the measured T sub loop against the transformation predicted by the current estimates of P sub I and P sub j. Because loop closure constraints are typically derived from high-quality sensor data, their information matrices are often significantly larger than those of odometry constraints, meaning they exert a strong corrective force during optimization, pulling the entire graph into alignment. Minimizing the global cost function requires solving a nonlinear optimization problem. Iterative methods like Gauss-Newton or Levenberg-Marquardt are employed. These methods linearize the error function around the current state estimate, requiring the computation of the Jacobian matrix and the Hessian matrix. Crucially, the Hessian matrix H, which approximates the second derivative of the cost function, is extremely sparse due to the local nature of most constraints. This sparsity is exploited using specialized solvers, such as Cholesky decomposition or conjugate gradient methods, which operate only on the non-zero elements. This sparse structure is what enables GraphSlam to scale effectively to thousands of poses and constraints.
Implementing GraphSlam relies heavily on established optimization frameworks designed to handle large, sparse systems. General Graph Optimization, or G2O, and Ceres Solver are two widely used open-source libraries. These frameworks provide standardized interfaces for defining nodes, edges, and error functions. G2O is particularly popular in robotics for its efficient handling of sparse block matrices common in pose-graph problems. Ceres Solver, developed by Google, offers broader applicability but is also highly effective for SLAM. These tools abstract the complex numerical linear algebra, allowing developers to focus on defining the geometric constraints and the sensor models accurately. GraphSlam provides superior global consistency compared to filtering methods because the optimization simultaneously adjusts all past poses based on all available measurements, including loop closures. The primary limitation is the computational cost associated with the batch optimization step, especially when the graph is updated frequently. Incremental smoothing and mapping techniques, such as ISAM, address this by only re-optimizing the relevant parts of the graph after a new measurement or loop closure, maintaining real-time performance while preserving the global consistency benefits of the graph structure. This hybrid approach represents the state-of-the-art in large-scale, real-time localization.